Hi, we are Indian brothers. In this present class, we are trying to consider the much needed consideration for the effect of location of poles on our stability considerations over here. And here I am just going to consider some much crucial considerations over here, and we would like to show you how do we say about the stability on that given considerations over here. In our previous analysis, we have considered our definition of a stability, and in our next class, we are just going to consider the much needed consideration for our the stability concepts with the help of some simple examples over there. In this present class, we are trying to consider how do we say about the poles over there and what is the definition of the poles I have already considered in a previous part over here. We do know that according to the transfer function we have got the CS divided by RS, that is the definition for our transfer function, and the GS will be our system, and the stability should be referring towards our given consideration for our GS, but that is directly considered with the help of our considered part over here. Now quite naturally, for that first condition, if you do apply the much needed impulse response in this case, now quite naturally the RS will be 1. Okay, now the CS will be quite naturally our GS. Now in this first consideration, if you do apply the step input over here, now quite naturally the GS will be 1 by S. Okay, and according to that considered part, you do know that if you do put the expression of GS is equal to 1 by S in our S plane, we are having our that pole is placed at the origin. Why? Because we do know, according to the definition of our much needed pole 0 plot over there, if you just do put the denominator part equal to 0, then that actually gives us the much needed poles over here. Now quite naturally in this case, we have considered the S plane over here. For that one, the S plane to have the equation of this one, which is sigma plus minus of our g omega. This sigma actually to give us the real part of our S plane, and the g omega will give us the imaginary part of our S plane. And quite naturally in this S plane we have considered that the S is equal to 0, and we have put that in the origin portion of our considered part. The solution in this case will be S is equal to 0. Now if we just put that in our S plane, we should say that the pole is placed at the origin of our S plane over here. Now what is the definition of our poles? We do know, according to the definition of our pole 0 plot in our first class or in our first chapter of our control systems over there. If you just do consider the denominator part that is equal to 0, that ultimately gives us the location of our poles over there, and we have do that accordingly over here. Now quite naturally the CS will be 1 by S. Now if you do apply the inverse Laplace on that given considered equation, if you do apply the inverse Laplace on this given equation, we will get back to the time domain equation over here, which is quite naturally the CS will become CT, and the 1 by S, if you do apply the inverse Laplace on this given 1 by S, we are having 1, and that we have just by using this one, we have considered this right hand side curve over here, which is CT is equal to 1. Now this one is applicable for our S plane, and this one is quite naturally applicable for our time domain analysis, And how do you get to that considered part? If you just do apply the inverse Laplace on this given equation, which is C is equal to 1 by S, ultimately we are having Ct is equal to 1, and we have considered this graph over here. Now quite naturally we can say that for the system, for our unit step response, we can say that the system is marginally stable. Why? Because this is not been present in our right hand side of our S-plane, or that is not been present in our left hand side of our S-plane as well. That is been placed in between these two considered part over here. So this pole is not placed in the left hand side of our S-plane, and that is not placed at the right hand side of our S-plane as well. That is being present in between these two stable unstable considerations over there. We do know that if the pole is placed at the left hand side of our given S-plane, then that will be considered as our stable, or the system is stable. Or in the other case, if we do shift the pole at the right hand side of our S-plane, then we can do comment or do say that the system is unstable. But in between this stable and unstable consideration, if the pole is being present in between this stable and unstable condition, then we can say that the system is marginally stable. So in this case, the system will be marginally stable over here. And I have already considered these over systems over there. Now this left hand side actually do give us the S-plane plot over here. And how do I get to that considered part? At the initial stage, we are having this transfer function which is Cs by Rs, which actually do give us the Gs. Now if you do apply the impulse response on this given equation, we do require to put that Rs is equal to 1. And if you just do put that, we are having Cs is equal to Gs. After this one, after putting or after considering the Rs is equal to 1, and for our given system we have considered that the system do have the unit step response over here. That is why the Gs will be 1 by S, and according to the consideration of our pole in this case, if you just do plot this given equation of Cs is equal to 1 by S, and we are actually considering our most important part, which is pole. And how do we put that plot in our given S-plane over here? Just do apply or do consider the denominator part, that will be equal to 0. And after we have considered this part is equal to 0, and at the S-plane we are having this pole that has been located over here, and we are having this equation, and after we do apply the inverse Laplace, we are having the Ct is equal to 1, and we have considered that waveform as well. Now quite naturally this waveform is not increasing, or that is not also being decreasing over here. And according to the definition of our transfer function, if you just do apply that the time t tends to infinity, and what seems to be the nature of our Ct, if that is being present in our much needed finite value, or if the output value or the Ct do have the finite value over here, then we can say that the system is stable. In another case, if the Ct is going towards infinity, if you just do say that time t tends to infinity, then that is the consideration for an unstable system. But over here, that is not increasing, and that is also not been decreasing over there, and throughout our operation the value for our given considered part will be 1. Now quite naturally we can say that we are having our marginally stable considerations over there. And in our next class we will discuss about these RAM systems over there. I hope you have totally understood up to this one. If you still have any doubts, please let us know in the comment section for better understanding. Do like, do share our videos, and keep following our channel. I want to say that this section is very important in terms of a stability point of view. So first of all, I want to remind you once again, I should start over here the transfer function definition will be Cs by Rs, that actually give us the Gs. And if you just do apply over here the impulse response in this given considered part, and that is the ultimate rule for the stability point of view. If you just do put that Rs is equal to 1, then we are having Cs is equal to Gs, and the system do have this response over here, and the system do have the transfer function which is 1 by s. Why? Because we are considering the step input over here, and if you just do plot the poles for our 1 by s factor over here, we are having this plot over here. And most importantly, if you do apply the inverse Laplace considered part over here, you are having Ct is equal to 1, and we have put that in our given considered part over here. And for both this S plane and for our Ct considered part, we can say that the system is marginally stable. Why? Because the Ct value is not increasing, or that is not been decreasing over there. In our previous classes, we have considered the mass needed definition of our stable and unstable considered part over here. So quite naturally, for the considered part, this system is marginally stable. Okay, I have already considered this portion over here. In our next class, we would like to discuss about this one over here. So just wait for my next class. That's it. Thank you and goodbye. If you like my video, so what are you waiting for? Please do subscribe my channel, hit the bell icon for more updates, and stay tuned to the channel. Thank you and goodbye.